Okay, so in this problem we have a block of mass and it has 2 kilograms, is initially at rest, so its velocity is its initial velocity is 0, and it's starting at the position x equals 0 meters. Okay, and it's on a slippery horizontal surface, and so it's going back and forth on a horizontal surface, and there's no friction, so we don't have to worry about friction, the friction force. Starting at time 0, a horizontal force, and this is a force as a function of time, is equal to beta minus alpha t times t, is applied to the block. So there's some force. And it's telling us that alpha is 6 newtons, Newton per second, and that b is 4 newtons. So the question is, what is the largest possible value of x reached by the block, and how long does it take to reach that point starting from time equals 0. Now there is a question B. We're not going to do part B. We're just going to do part A. Once you've done like the first part of this problem, then the second part is pretty easy. Okay, so we're just gonna focus on the force, how far did the object go, and then how long did it take to get there. Now, in these problems, of course, there's a quote-unquote traditional way of solving it, and you can see here, this is a traditional way where you have to remember your equations and kind of lay them all out, manipulate them, etc. Know like where all your values go, manipulate the equations, and then of course get your right answer. This is not how I do it. I mean, I sometimes do it like this, but mostly I use kind of like intuition, common sense, and a strong sense or a sense of the mathematics behind it. Okay, so I'm going to use calculus, just as I've said before, calculus, geometry, trigonometry, things like that, to solve these problems. Okay, so instead of going through this, we're going to try to solve it in a more intuitive approach. Okay, so this is called a sliding block, and what I like to do, of course, is just sketch out the problem, and you can see here. Let me just do this. Here's our block right here. It's 2 kilograms, that's its mass, and it's going to be moving to the right, and you can see the v0, or the initial velocity, is 0 meters per second because it's at rest, and I wrote the origin, which is right here. So that's the origin of the mass, and it's going to be moving to the right. And what the problem said is it's moving. It says it has a force applied to it. The force is a function of time, and the force is now it told us in alpha and beta values, but if you just swap them in, you'll get negative 6t plus 4. Okay, and that's in newtons. So if you plug in some t like 5, that'd be 5 times 6 is 30 minus 30, or negative 30, and then plus 4 is 24, no, 26, negative 26. So it'd be negative 26 newtons. So if you plug in a 5, you get out negative 26 newtons. Great. Okay, so that's cool and everything. But what I really like to know is so it wants to know like how far did you go, the time required. Now, how far? What does that mean? Well, that means how far in x. So I need some position. I would like to have. What I'd like to do is I'd like to know the position. We'll call r the position as a function of time, right? So if I plugged in like 3, for example, it would pop out, I don't know, like 100 meters or something. Okay, so that's what I would like. I would like to have a function where I could pass in the time, and it just tells me how far did it go. Now, do I have that right now? No, I don't. But that's kind of like where I would like to go, because it says how far did you go. So if I knew how to model this, block, model it meaning if I knew the actual function behind it, the actual kinematic function behind it, then I could just plug in any value that I want. Okay. So then the question is, well, how can I get that? Well, we do have. Let me just erase this. We do have f, right? That's really the only thing we have is f. So we have f. Now, as you may remember, Newton's second equation, the sum of the forces, right? Sum of the forces in whatever direction. Here we have x. We're just moving in the x direction. is, so it equals mass times acceleration, right? In x. Because x is a vector, and then the force is also a vector. Okay, so this says that force is equal to the mass times acceleration. Well, I have the force, I have that function, and I also have mass. So from that, we can derive acceleration, right? We have F, we have M, we just need to find A. Now you might be like, why do we need to find A? Well, if you have F, you can find A, which is acceleration, right? And then after that, you can take acceleration and you can integrate it, and you can find velocity. And then after that, you can integrate it again and find position. Favor. So this is how you go from force to acceleration to velocity to position. And then once you have position in, you can just plug in whatever time you want, and you'll get how far that you went, which is what we're looking for. Okay, so we know what force is. So force is negative 6t plus 4, right? So force is equal to negative 6t plus 4. And so let's look over here. Let's go on this side. So it's F equals ma, and I know and I have m, right? Sorry, I'm looking for a, so I'm just going to divide by m, right? Divide by that, and then we have acceleration is equal to force over mass. So all I have to do is divide the force by mass. So this is the force, negative 6t plus 4. I'm going to divide the whole thing by the mass, which is 2. And if you do that, you're going to end up with acceleration, your acceleration function, acceleration as a function of time, which is negative t plus 2. Negative 3t plus 2, right? Because 2 goes into 6, 3, 2 goes into 4, 2, right? And now we have negative 3 plus 2. Okay, so let's just rewrite F. We'll put it right here. F equals negative 6 plus 4. So there we go. So let me just highlight this. So here's our F. Oh, I forgot my T. It's a function of time. And now I have acceleration. Let me highlight that one as well too. And this is they're both obviously functions of time. Okay, that's cool. So now after that, what I could do is I could integrate A and find velocity. So let's try that. Okay, so if you integrate A, right? So this is just a normal integration. You would take the 3t, you take half of 3. So this is velocity then as a function of time. It's negative 1.5 because it's half of 3. You take t, make it t squared, and then you add 2t. You integrate 2, which becomes 2t. And now you have to put on your initial values. What's the initial velocity? Well, it says it was starting at rest, right? So that means it's 0. So you could just say 0 if you wanted to, or just erase it. Okay, or just erase it. So there we go. So now we have velocity as a function of time. Okay, and so then we can just keep going and say, okay, well now I just want position. So if I want that, well, then I just integrate v and get position. So r equals, so now I have to integrate v. And so the negative 1.5 t squared becomes, I have to do 1.5, I have to divide it by 3. So that becomes negative 0.5. And the t squared becomes t cubed. And then the 2t, I have to take half of 2, which is 1, or just t, and then t becomes squared, plus t squared. And now I need to know the initial position in x, which is 0, right? So we're at the starting point, so we're at 0. So that's it. So there you go. So how did I get, let me just do this, hold on a second. How did I get from here to here? I divided by 2. How did I get from here to here? I integrated. And how did I get from here to here? I integrated. Okay? So once again, I just took a problem that just gave me just one function, and then just using my knowledge of, calculus or algebra, in this case here, you can derive all the formulas. Okay, so the question is, so in this R, if you knew R, so now you could say, oh, R, I could pass in my time, like, 3 seconds, and it'll tell me, I win 100 meters or something like that, okay? The problem is I don't know what the time is of when did it, so at its highest point, I don't know R. Okay, so what we could do is this. Let me just erase this guy. Let's plot R out. Let's plot R, okay? So if I do this, and we do this, and this is R, the position in X as a function of time, okay? So if you were to plot this graph, I'm not going to plot it exactly, but, something like this. And it has some peak, right? There's some peak. There's some peak like right there. We'll call this like little t or something like that, or T1. Okay? So if you were to plot R, if you were to plot this function, that is this. So this function is negative 0.5 t cubed plus t squared. That is this function. Maybe I'll make it blue just to make it more obvious. Okay? Sorry. That's that function. So great. So this is how this object moves in X. So you can see, let me make this red. So initially, starts out at 0 in X, and it's going up, 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 or farther away. It's not going far. It's not going up. It's going farther and farther away from the origin. And at this point here, it's as far away as it's going to go. And the question was, what's the farthest distance it goes? So it's this distance right here. So what is this? So we have two graphs, right? We have the blue, this blue area here, which is, I'll just do it again. We have that graph, which is negative 0.5 t cubed plus t squared. We have another function, which is this one. It's going across like that. And I want to know, where do they interact? Now, you may say, well, I don't know what that is. Yeah, but you do know something though. This is where the slope of the line becomes 0. Where the slope of the line becomes 0. So what you could do is you could say, where is the slope at? Well, the slope is the velocity. So what I could say is, I want to take the velocity. Velocity is negative 1.5 t squared plus 2t, right? And I want to know, where does negative 1.5 t squared plus 2t, where does that equal 0? What time is that? And so time will pop out. So if you solve this, negative 1.5 t squared plus 2t equals 0, you get a t of 1.33. 1.33 seconds, okay? So this is the time. So what I did is I did this graph, but see, I don't know, for example, here, this red, I don't know what this line is. But I do know where it is in the velocity graph. So in the velocity graph, I do know it, because this is where the slope of negative 0.5 t cubed plus 2 t squared is 0, right? That's its slope. So I set the blue line equal to, sorry, I actually don't set the blue line. I set the negative 1.5 right here. Change this one. This is the velocity graph. I set that one equal to 0. Out pops 1.33, t equals 1.33, and so that's this, t1, or whatever you want to call it, is 1.33 seconds. Okay, that's the time at which the slope at the top is 0. The slope at the top is 0. And remember, the slope of the position function is velocity. The slope of the position function is velocity. Okay, great. So now I know the time at the highest point is 1.33. So now if you know that, then the rest is just easy. So my function r, it's r as a function of time. Remember that is negative 0.5 t cubed plus t squared plus t squared. And now all I have to do is pop in t. So now I have to do r at 1.33 seconds is equal to 0.5, and this is 1.33 cubed. Yikes, that looks bad. Plus 1.33 squared. Okay, we're just gonna replace those values. This is a 5. This is a negative. And if you do your math, you end up with 0.59. 0.59 meters. Okay. And so that's basically it. So we end up with this at this time, 1.33 seconds later, I end up as far away as possible, which is 0.59, almost 0.60 meters away. So just in recap, instead of so actually, hold on a second. 1.33 and 0.59. So let's go up here at this one, and you can see here 1.3 seconds. That's what I got, and then 0.5. That's how far away it is. See x max and time max. Okay, so we got the same answers. But you just have to ask yourself, what is more intuitive? Like this answer here that they gave, right? Is this more intuitive? Or is it more intuitive to just go, oh, well, I have force. I just need to turn that force function into the acceleration function. How do you do that? Just divide by 2, the mass. Oh, how do you take the acceleration function and go to velocity? Integrate. How do you go from velocity to position? Integrate. And then once you have these functions, then you can kind of just use some basic knowledge of physics to figure out, oh, okay, I have to take my velocity, set it to 0. The velocity function set to 0, grab my time, and then I plug my time value into my position function, and get my final position. So that's it. Anyway, I like I said, I find this solution, this way of attacking the problem, much more intuitive than the other way, and it just makes more sense to me. Anyway, that's it.